Okay, so in this lecture, we're going to begin our study of more advanced integration techniques. And the technique we will learn today is called integration by parts. Before starting this, however, it's going to be very important that read through section 8.1, which kind of summarizes all of the techniques that we've learned thus far. And it has a nice little table that you can just take a picture of and just use that when you're doing these. Okay, so this entire section, this entire lecture is based off of the following theorem. Okay. And it says that if U and V are functions of X, they also have, so functions of X, and have continuous derivatives, then the integral of U dV is equal to U times V minus the integral from V du. Okay. Now, this might not seem very useful, but trust me, it is. And it's motivated by the chain rule, like so many things in calculus, so maybe like a proof idea. So maybe if we look at the derivative with respect to x of, say, u v, and these are both functions of x, then we can write this as, say, maybe du dx times v plus, or I'll say v times this, just make it look nicer. So v du dx plus u dv dx, right? Which is chain product rule. But then once we have this equation, we can integrate both sides of this, right? And we get that uv is equal to the integral of v du dx u dv dx dx, which simplifies to v du plus the integral of u dv. And then if we move v du to the other side of the equation, we get that uv minus the integral from v du is equal to the integral of u dv. Okay, so that's more or less the proof idea, right? Now, how can this be used? Well, in particular, like not in particular, this is useful if you look at this side of the equation, the integral of u dv. If you have a function times the derivative of another function, you then have a technique for maybe simplifying it into two smaller pieces. So when you have a product of functions, this integration by parts becomes really useful. So as a simple first example, let's look at the integral of x dx dx. Okay, so the integral of x times ex dx. Now notice here we have a product of functions, and we would not normally have any integration rules for this problem, right? But I notice now that I have x and then ex dx. So what I can say now is this product, I can say let u be equal to x and dv equal to u to the power x dx. Once I do that, I have the integral of u dv, which means that I can write out this equation here. I like to first, however, find all the variables needed. For example, I have u and I have dv, I'm missing v and du. But these are easy to find. If we take the derivative on both sides here, we get that du is equal to dx. And then if we integrate both sides of this, we get that v is equal to ex. So you integrate both sides of this in order to solve for v, right? Because this is like the derivative of v. Okay. So now that we have all of our pieces, we have that this is now equal to u times v, u times v, minus the integral of v du. And this integral here is easy to work with. That's just e to the power x, right? So then altogether, we have, that's the answer. So hopefully that illustrated that this can simplify integrals that we wouldn't normally know how to deal with. Okay, so it's a very important, useful rule to know. So the idea maybe that I should warn you about ahead of time is that if I were you, I would say choose dv to be the more complicated part of the integral, the more complicated expression. Right? Because that complicated expression you can integrate and then well, just in practice, that's kind of what I've always done. Okay. But it doesn't matter. This holds for any combination. So it doesn't matter how you choose your u and your v's. You just want to choose them so that it makes life easier, right? So that's important to know. So let's look at a few more examples. Let's look at the integral of x squared times natural log x dx. Okay, so we don't know how to integrate natural log x. So I immediately have a choice to make. And and I'm going to say that I know how to take the derivative of that, and to integrate x squared dx doesn't seem too bad, so maybe I can say u to be natural log x and dv equal to x squared dx. So then du is equal to 1 over x dx. Okay. And then v is equal to 1/2 x. No, 1/3, sorry. X to the power 3. I had to integrate both sides of that. Okay, so I take the integral on both sides, get v is equal to that. So now, this is going to be u times v, so it's like x cubed natural log of x over 3, so it's u times v minus the integral of v du. So pull out the 1/3. So v is x times 1 over x would just be x squared dx. So then all together, right here, and we're going to have there. Okay, so again, this would have been more or less impossible for us to deal with before, and now it's not so bad. Okay, so maybe now we're going to make one a little bit more tricky. Say the integral from 0 to 1 now of arc sine x dx. Now this one, there's no product. However, it's still okay. So why would this be okay? Well, let's find out what the antiderivative of this is, and then plug it in, and then use the definite integral part. But we're going to focus on finding the antiderivative, and I'll show you how we can still use this theorem. So I just want to know the antiderivative. Oh no, it's x arc sine. Sorry. No, it's just arc sine. Okay. So if I take u to be equal to arc sine x and dv equals to dx, can we use this, right? We can, it's a theorem. It's always true for any choices. All right, so du, so the derivative of arc sine is 1 minus x. So 1 over root 1 minus x squared. And then v is equal to x. So then this indefinite integral is going to be uv, so x times arc sine x, minus the integral of v du. So, oh yeah, there's a dx here. Yeah. Derivative, I forgot to write the dx. Du, okay. So v du is now x dx all over root 1 minus x squared. Okay. So then we need to know what this piece is. And now in order to do this piece, we have to kind of reference back old techniques. So if we say, if we just let u equal 1 minus x squared, then du is equal to minus 2x dx. So that means that minus 1/2 du equal to x dx. This is just like normal u substitution we're doing over here. The normal u sub so we have x times dx is negative 1/2 du. So I'm going to take out that negative 1/2 and that it'll become positive. And then on the inside, we'll have, so that's like u to the square root. So u to the power of minus 1/2 du. Add 1 to that. So arc sine x, so we have half. So half divided by a half, that'll go away. This just be plus u to the power of 1/2 plus c. So the u is really that. So arc sine x plus square root of 1 minus x squared all plus c. So that's my antiderivative, but we're looking at the definite integral in this problem. So we just use that information. So x arc sine x plus root 1 minus x squared from x equals 0 to x equals 1. So 1 times arc sine of 1. So arc sine is the angle in radians that gives you the value 1. So that's going to be pi over 2. That's the angle in between 0 and pi that gives you 1. So arc sine of 1 is pi over 2. 1 minus x squared, that's 0, so it goes away. And then 0 here times that goes away. But then 0 here, the root 1, so yeah. Pi over 2 plus 1. Okay, so that would be an application of integration by parts for a single function, which again, you can still do. Now, let's look at an example with repeated applications of integration by parts. All right, so let's look at integral x squared sine x dx. Okay, so I guess the strategy is that if you choose your u appropriately here, and you're always taking derivatives of u, if you have something like a polynomial function in there, you let that be your u, and you just keep on taking derivatives, eventually it goes away. And you'll see that in this problem here. So let u be x squared and dv equals sine x dx. Okay, so then du is equal to 2x dx, and v is equal to, so if you integrate both sides here, you get negative cosine x. So plugging in, u times v is just minus x squared times cosine x minus the integral of v du. So v du, there's a negative 2 that I can take out in front of the integrand, so minus negative, well, I'll just write it out. So, right, cosine x, 2x, dx. So I'm going to just take out that -2, and it'll become positive. And then we have x cosine x dx. And here, with x cosine x dx, we can use integration by parts on that part. So we have u is equal to x, and dv equal to cosine x dx, and du is equal to dx, and v is equal to sine x. So now, plugging back in and being careful that 2 is multiplying everything. So negative x squared cosine x plus 2 times this integral. So uv is x sine x minus v du, or the integral of v du. So, and finally, we got to a simple integral that we can apply the standard integration techniques to. So all together, the 2 multiplies that, x sine x, and then 2 multiplies the integral of this. So the integral of sine is negative cosine, and there'll be negative cosine, so 2, so this would be plus 2 cosine x. Let's see, because the negative makes it positive, and the 2 multiplies in, and all together, there you go. Okay. Okay, so from section 8.2, homework, suggested homework is going to be 11 through 33, and then 23 through 52. Okay. And that would be it for integration by parts.